Hi everyone. Today we're looking at this topic right here, spontaneous reaction. Now let's go quickly. Okay, this is sort of like an extension to topic 5, thermodynamics. I think we'll end up looking at heat of formation. So this is pretty much the exact continuation of what's going on afterwards. Well, hey, let's not wait and let's get on to it. So, what is a spontaneous reaction? Now, we kind of talked about this before. When a reaction is spontaneous, that means it can occur with very, very minimal assistance. Maybe just a little bit of a flame, a little kickstarter, and the reaction will go woof to completion. Now, not all reactions are like that. Okay, a lot of reactions actually are non-spontaneous than spontaneous, where you have to continuously fuel the reaction in order to go to completion. Okay, so that's what a spontaneous reaction is. Okay, is a reaction that requires very little outside energy. Okay, now all the examples that we're going to talk about today is under SATP. Now, you remember what SATP means? That means 1 atmospheric pressure and 25 degrees Celsius. All right, so everything that we're talking about is under SATP, and it should be, because most experiments that are done are usually done under 1 atmospheric pressure. They're done usually at room temperature. Okay, very rarely would you see somebody doing an experiment at boiling point or at melting point. That's too extreme. Who's going to do that? All right, let's do a little recall right here. Okay, something that we learned back in the days. I believe it was January, just before the final exam. We mentioned the fact that reaction that releases heat are said to be exothermic. Now, when you calculate the heat of formation, delta H should be less than 0. It should be a negative number. Okay? And reaction that absorbs heat, so the surrounding must be cold then, is an endothermic reaction, where the heat of formation will give you a result of delta H greater than 0. Right? Now, what does nature favor? Exothermic or endothermic? Now, if you remember what I said back in January, we said that nature favors exothermic reaction. Nature likes it, I guess, negative for enthalpy. Okay? Like this reaction right here. This is the combustion of octane gas. This is exactly what's happening in the engine of a vehicle. And as you can see, energy is in the product side, meaning that this reaction is exothermic. As a result, we say it was spontaneous, that this reaction will happen with very minimal outside assistance. Now we know that. Okay, this is a combustion reaction. All combustion reactions are spontaneous. That's just the way it is. But are all reactions spontaneous? The answer is yes, even when they're endothermic. Take a look at this reaction. Now, I don't remember if I demonstrated this reaction with you. I might have. Okay, it's been too long. If I didn't, I'm sorry. Okay, but what I would have done is I would have took this stuff called ammonium nitrate, and I would mix it with barium hydroxide. Okay, I'm going to draw it right here. I will take a meter stick. Okay, under the meter stick, I will put some water here, a drop of water, and on top of the drop of water, I will put a little beaker. Inside this beaker, I will have these two guys mixed. Okay, so why would I want to do that? It's because when these guys are mixing, it actually takes energy from the surrounding and use it. So as you can see, energy is on the reactant side, meaning that this reaction is endothermic. What does that also mean? It also means that this reaction It's going to absorb heat. The surrounding is going to be very, very cold. So cold that this drop of water will turn to ice and this beaker will be stuck onto this meter stick. Okay, what I would have done is I would have flipped this around to see if this will drop to the ground via gravity. I'm not sure if I did that with you, or I might have done it with one class and didn't do it with the other, or I might have done it but it was an epic fail and nobody remembered it. Obviously, if it was an epic fail, I wouldn't remember it. I only remember successful things, right? But whatever, okay? But this is an endothermic reaction. This is an exothermic reaction, and we said that exothermic reactions are spontaneous. Check this out. This is an endothermic reaction, but it was also spontaneous. All I had to do was mix these guys with a stir stick. Okay, I didn't have to keep pumping energy into the system to get this to react. No, it was spontaneous. It was endothermic. Why? I thought nature favors exothermic. How come endothermic reaction is also spontaneous in this case? Well, the answer is very simple. The answer is I didn't tell you the whole story back in the days. Okay, back in January, I only told you half the story. The other half is right here. Enthalpy is not the only factor that determines spontaneity. There's one more factor, and that's called entropy. Delta S. Okay? I know, another term. Sounds so similar. But yes, enthalpy and entropy together determines spontaneity. Okay? The question is, what are entropy? Well, entropy is a measurement of how unorganized or how random something is. Or some people would say how disordered something is. So if somebody were to tell you that, hey, your bedroom is high in entropy. What does that mean? That means your room is a mess. It's disorder. Everything is put in random places. Sort of like my kid's room. Somebody's gonna get in trouble. Right, so that's entropy. So when disorder increases, so the messier something is, the greater the entropy. And what does nature favors? Nature actually favors randomness. Nature favors a positive delta S. Wow. And that's not surprising. I have a couple of examples that will illustrate that. Okay? Example number 1. You have some sort of crystal solute. Okay? It's a crystal. It's a solid. You put it in a solvent, water. What will happen to this solute? Well, it dissolves, right? It will dissolve into its cation and anion counterpart. Is that more, I guess, is the system more disorder or less disorder? Okay, as you can see, this is actually a physical property thing. And I can tell you right now, when a crystal dissolves, you're having ions all over the place. That is an increase in entropy. Okay, is you having an increase of disorderness because now things are more spread out. Right? The ions are spread out. Before, the ions was intact in a structure of lattice. Because you dissolved it in water or dissolved it in some sort of solvent, everything is more spread out. Increases in entropy, increases in disorderness. Right? Example number 2. You have some sort of liquid. Okay? Under heat, it gets evaporated into a gas. Again, entropy increase. Because now these gas particles are taking up more space, more disperse. Entropy increases. So both cases right here indicate things that are more random, and nature likes that. Nature favors that. So when delta S is greater than 0 in a reaction, the change is also spontaneous, meaning that when you have a reaction A becoming B, if B is more random than A in terms of structure-wise, in terms of its physical property, nature will favor that situation. Okay? Now, here's something that we will see later on, what we will use later on when we start doing some example problem, is that delta S naught is equal to the sum of the molar amount of delta S product minus the sum of the molar delta S reactant. It looks familiar, doesn't it? Okay, the last time we saw something like this, instead of delta S, it was delta H. Don't worry, you'll see that again too. Alright, so that's entropy. Hopefully you kind of understood that. So in summary, okay, delta S and delta H has to work together to help us predict whether something is spontaneous or not. You have a reaction. You want to know if it's spontaneous? You need to look at both of these factors. Okay, back in January, we just looked at this and we say, oh, negative delta H, spontaneous. Not no more, because that might not always be the case. Okay, because when delta H is exothermic and when delta S is pretty random, yeah, spontaneous. And the other way works too. If this was endothermic, but if delta S was not very random, then it's non-spontaneous. So when we go back to this reaction right here, yes, delta H was greater than 0, but delta S was also greater than 0. That's why this reaction can be spontaneous. Okay? But if delta H was greater than 0, but delta S wasn't, then it's non-spontaneous for sure. That situation with the ammonia was this situation. Sorry, it was this situation. Okay, where, yeah, it's endothermic, but then randomness increases. Now, the question is, how do we know? Even with this situation, how do we know it's spontaneous? Even with this situation, how do we know it's spontaneous? Under this situation, it's for sure spontaneous. Under this situation, it's for sure non-spontaneous, but what do we do with this? Well, that's when this guy comes into play, because temperature affect this guy, Gibbs free energy. Okay, discovered, of course, by this dude named, I guess, Gibbs, right? I don't remember his first name, and for some reasons, maybe not. Yeah, I remember now. Josiah Gibbs. Okay. He's actually an American, believe it or not. So he came up with this stuff called Gibbs free energy. By calculating Gibbs free energy, you can determine if a reaction is going to be spontaneous or not. Now the question is how, right? Here it is. Gibbs free energy, delta G. First we have delta H, then we have delta S, now we have delta G. Alright, so when delta G is less than 0, so if delta G was a negative number, then it's going to be spontaneous. Okay, no doubt. So, to calculate delta G, this is the formula that you're going to use. Okay, delta G is always kilojoules. Now, Gibbs free energy is not the same thing as Von energy. Okay, it's free energy. Okay, it's different from, I guess you would say, call it thermal energy. It's not thermal energy. Okay, it's free energy. Now that's obviously something that I guess you will read about later on. Okay, but our job today is to discover if something is spontaneous or not. But that's not really important anyways. But yeah, that's measuring kilojoules. Now, delta H we saw back in January, and that's measuring kilojoules. Okay, delta S is actually measured in kilojoules per Kelvin. Okay, where can we find delta S? Well, you can find it in any CRC handbook. You can find it in your IB constants booklet. Okay, for the sake of today, I'm not going to get you guys to look over these values. I'm just going to give it to you in terms of question by question, so that'll save you a lot of time. So just to let you know, these numbers, okay, values for every chemical is in our CRC handbook. Okay, now temperature right here is measured in Kelvin. So if they're not, make it Kelvin, because you cannot have a negative temperature or else this whole equation will be garbage. Okay, the whole idea of degree Kelvin is to eliminate negative temperature. That's why we can't use Celsius. We don't want to use Fahrenheit. Okay, we want to use Kelvin. So let's do this question. Question number 1. I want to know if this reaction is spontaneous or not under SATP. Oh, thank goodness we learned organic chemistry. Imagine if I give you this question and you didn't learn organic chemistry yet. My God, that would be disastrous. Ethene, right? That is C2H4. What am I going to do to it? Well, it says I'm going to hydrogenate it. So I'm reacting C2H4 with hydrogen gas. What am I going to get? You're going to get C2H6. Okay? The double bond here will break. As a result, you have an alkane. Okay? All right. It's very important actually to put in the states, because when you look at the CRC handbook, some chemical are based on state. Now for this one, it's going to be gas for sure, because these are very small hydrocarbon, as you remember, have a very, 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 very low boiling point. Okay, so they are usually in gaseous order. Anyway, so that is the reaction. So what are we going to do? We want to know if this is spontaneous. So remember, if delta G is negative, spontaneous. If delta G end up being positive, it's non-spontaneous. So let's calculate delta G. So delta G, okay, is equal to delta H minus T times delta S. Okay, so we're talking about standard conditions, so therefore these not has to be in place. Okay, all right, let's calculate each entity one by one. Well, let me just give you some values, because I don't need you to get the CRC handbook, but I will give you the values. Okay, for C2H6 right here, delta H is equal to negative 84.5 kilojoules per mole. Okay, C2H4 is equal to 51.9 kilojoules per mole. Okay, hydrogen is a diatomic molecule. Anybody remember what happens? What's the enthalpy for diatomic molecule? Now, if you don't remember, don't worry about it. I'm not quizzing you or anything. It's going to be 0. Okay, 0 kilojoules per mole. Hopefully that is just something that you always remember, because if you're going to go to your CRC handbook, or if you're going to go to your IB constant booklet, they're not going to give you H2. They're not going to give you O2. They're not going to give you Cl2, because they expect you to know that these diatomic gases are going to be 0. If you don't remember, don't worry about it. All right, let me give you delta S as well. Okay, delta S for ethene is 219.8 joules per mole Kelvin. Okay. For hydrogen, it's not zero for delta S. In terms of randomness, the formation of hydrogen actually has a number. It actually has a value. And that's 130.6 joules per mole Kelvin. Okay. And for C2H6, delta S is 229.5 joules per mole Kelvin. So in terms of randomness, okay, you can see that all three numbers are positive. What that means is that the formation of ethene, the formation of hydrogen gas, and the formation of ethane are all favoring what nature wants. Okay, that the creation of these guys are all positive value, meaning that what you're using to make these guys are less random, if you know what I mean. Okay, all right, that's enough, I guess, information to calculate. Just put in the color to calculate delta H and delta S, and we know what T is. T is 298. So let's go ahead and calculate delta H. If you remember how to calculate delta H, it is the sum of the product, subtract the sum of the reactants, and make sure you take mole into account. The good thing is here is that the molar ratio is 1 to 1 to 1. So that's something that you don't have to worry much about, right? Good thing. So let's calculate this together. So this is going to be 1 times negative 84.5 kilojoules per mole. Moles will cancel. Okay, because this is mole. Minus 1 mole times 51.9 kilojoules per mole. Again, mole cancel. Minus 1 mole times 0. That's a good thing. I like that. Okay. So really you're putting this together, and what would the answer be? Get off. Try my calculator. Yes, I'm basically typing this in as you are. Oh wait, hold on. I made a mistake here. This should be plus. It's the sum. My goodness. But it doesn't really matter here because this is going to be a zero entity anyway, so let me make sure. All right, so my calculator says negative 136.4 kilojoules. So that is delta H. Okay, hopefully I didn't make any mistakes. If I did, I'm so sorry. Delta S. Okay, the idea here, the same thing. You're really just using different values. So again, 1 mole times 229.5 joules per mole K. Moles cancel, so you're left with joules per Kelvin minus 1 mole times 219.8 joules per mole dot Kelvin. Okay, plus 1 mole. Okay, this time it's not a 0. That means you have to do more work. There you go. Okay. Let's hope I actually set this up correctly, or else I'm going to be making a fool out of myself again. Alright, so let me punch this into my calculator, and I should get a negative number. Alright, I got negative 120.9 joules per mole, per Kelvin. Okay. All right. Hey, now I'm ready. Now I'm ready to put this into our delta G formula. But I need to do one more thing first. I wonder if you guys kind of figure it out what I need to do first. Okay? Yeah, if you're wondering, hey, delta H is in kilojoules. Delta S is in joules. I can't just subtract these guys. Okay? I have to make sure that they're consistent. Well, guess what? We want delta G to be in kilojoules. We do. Okay? Delta G should be in kilojoules. So the logical thing here is make this kilojoules. Okay, so don't forget that, because a lot of people on tests, they forget about this. Maybe under a lot of pressure, they decided that, oh, I don't remember that these guys are not in the same unit. But yeah, they're not in the same unit. The CRC handbook measured these entropy under joules, and they measure enthalpy using kilojoules. I'm not sure why they do that, but they really should keep it the same. Okay, enough of that. Let's do delta G. Delta G is equal to negative 136.4 kilojoules minus, okay, 298. Okay, remember, it has to be in Kelvin. That's 25 degrees Celsius times negative 0.1209 kilojoules per Kelvin. And we know for a fact that Kelvin and Kelvin will cross out. Okay, so our answer should be in kilojoules. And let me just punch this in. Negative plus negative and minus negative will be a positive. So therefore you're adding these two number, and my answer should be negative 104 kilojoules. So hey, make sure you check my work. Okay, I may be wrong. Now, the number is not important, because the question is not asking me for what delta G is. What is the free energy for this reaction? I'm not asking for free energy. I'm asking to see if this reaction is spontaneous. Is it spontaneous? You can bet your bottom dollar it's spontaneous. How do I know? This guy's a negative number. Delta G is negative. Huh. As a result, this reaction is actually spontaneous. Okay, hydrogenation reactions are spontaneous. So if you take some sort of alkene, an unsaturated hydrocarbon, reacting it with hydrogen gas will spontaneously give you a saturated hydrocarbon. All right, so hey, that's how you do these things. So yeah, it seems like a lot of work. There seems to be a lot of places where you can make mistakes, but at the very end, I do hope that you do check over what you know, okay, and figure out everything else on your own. All right, I have another question here for you. Example 2. Oh, this is a cool question. Okay, I do have answers for this because I really want you to know how to do this on your own. So I'm just going to give you the values, and I'm going to give you the answer, and hopefully you got the same answer I got. Yeah, this reaction is cool. Okay, I picked this reaction for a reason, because it's disgusting. This is urea. Okay, that's urea. we know where to find urea, right? If you react urea with water, not dissolving it in water, don't take your PP and dissolve it in water and expect this to happen. Okay, that's not gonna happen. You're not dissolving this. You're not mixing this, but you're reacting water with this. Okay, there's gonna have to be a catalyst involved. I'm not gonna show you what that is, but if you were to react these two things, you're actually gonna get ammonia. That's how you get ammonia. And the disgusting thing about this reaction is that long time ago, that's how people, that's how people make dyes. If any one of you are into dyeing their hair and stuff like that, you know one of the dyeing solution is ammonia based, right? If you don't, sniff it, smell it. It's disgusting. That's because there's ammonia in it. So, long time ago, they know about dye. Okay? I'm not sure if they dye their hair, but they are dyeing things. And they know to use ammonia. And to get ammonia, they need to get urea to react with water. I'm pretty sure you know what I'm trying to get to here. Yes, they would try to react urine with water to dye stuff. How crazy is that, huh? Anyway, I want to know if this reaction is spontaneous, okay? And in this guy, I actually do care about the Gibbs free energy that you get from this. So I'm gonna give you values here, and I'm gonna also give you the answer. So let me give you delta S for these guys. So I'm gonna so red is delta S. Okay. So urea is actually 173.8 joules per mole Kelvin. Water is 69.96 joules per mole Kelvin. Carbon dioxide as a gas is 213.6 joules per mole Kelvin. And ammonia is 192.5 joules. Joules per mole Kelvin. Okay? I hope I got everything right. Imagine if I give you the wrong number and you keep getting the wrong answer. My gosh. Blue is delta H. Okay? Delta H for urea is actually an exothermic thing. Okay? Water. Okay. Carbon dioxide. These numbers you should be very familiar with because we always do combustion reaction when we're doing thermodynamics. And ammonia is negative 460. I hope I'm right. But again, you can easily find these numbers on the internet. Okay, just type in, delta H for urea. It'll spit off 319.2. All right. Guess that's all there is. Okay. Oh, just one more thing about this question. I guess I forgot to tell you is that this reaction is happening at SATP. Now, without me writing that, I think you guys should all get that. Okay, it's not like I'm doing this reaction anywhere else. At the same time, if you think about it, you can't really use these values at all if it's not SATP, right? Because these values are all not value. All right, I actually have the answer for this. Okay, I worked out the answer a long time ago, and I got 13 kilojoules. So this reaction is non-spontaneous. So hopefully you got the same thing. Okay. All right, so you guys can do this question on your own. practice with those delta G questions, and that's exactly what delta G is for. It's really for figuring out to see if a reaction or any reaction is spontaneous or not. Now, the second thing that I want to show you, okay, deals with equilibrium. Yes, I'm sorry, but yeah, we're going to have to look at equilibrium. At least, how does that relate to delta G? So, in an equilibrium reaction, where the reaction can go forward and backward, when delta G is a negative number, okay, the reaction is obviously spontaneous in the forward direction. Okay, so the reaction going forward is spontaneous. If delta G is a positive number, the reaction is non-spontaneous. However, it is spontaneous if you're looking at the reverse reaction. If you were to go to the left side, the reaction will be spontaneous. Okay? So if you have a reaction and you calculate delta G, and delta G is a negative number, well, you know what? The reaction actually is going forward, meaning that the reaction have actually not reached equilibrium. If delta G is a positive number, the opposite happens, that the reaction is also not equilibrium. There's too much product or something that the reaction right now is going backwards. What we want to see is this. When delta G is equal to 0, okay, that means this reaction is at equilibrium. No further action needs to take place because the amount of product being made equals the amount of reactant is being made. And as long as it satisfies the Kc value, remember Kc? Then the reaction is all good. Delta G will equal nothing. Now, how does this pan out? What is this? Why is this useful? Why do scientists want to know about this? Well, it has something to do with temperature. Because if delta G is equal to 0, let me just prove this to you. Okay, eventually we'll end up here. So this is the equation, right? If delta G is equal to 0, that means delta H minus T delta S can be rearranged. Okay? Can be rearranged like this, where you have T equals to delta H. Okay, notice that I kind of just move this to the other side. Okay, and let me just do this thing strategically, because some people hate it when I skip step in mathematical operation. Alright, so all I did was move this to the other side so it becomes a positive. And if I want to find out what temperature is really just delta H divided by delta S. Okay? Now, why is this important? It's important because you're looking at or finding out a specific temperature where this reaction will take place. So we're not looking at SATP here. We're actually looking at a specific value based on, of course, SATP. Because if you are doing a reaction under standard condition, there's a specific temperature where the reaction will happen at an instant. Like, for example, if I were to ask you, hey, what's the boiling point of water? A lot of you will say 100. How do people know that other than doing the experiment? Can they find that out using data? Of course we can. In fact, we're going to do that right now for example 3. I have a reaction right here. Liquid water evaporating to give you gaseous water. We know this reaction is not a forward one-way reaction because the reaction can always go back. So it's an equilibrium reaction. Okay? because it's an equilibrium reaction, we are able to use this because at equilibrium, delta G is equal to 0, right? So when delta G is equal to 0, we can manipulate their equation to solve for T. And this is exactly what the question is asking me to find. They're asking me to find T. Calculate the boiling point of water at 1 atmosphere. What is the boiling point of this? Now, we all know what the answer is. The answer is 100. You're not going to get dead on 100 with the data that you're getting right now. Okay, but you're going to get a number close to 100, and let me show you how. Basically, T is equal to delta H over delta S. Okay? This T is obviously based on this reaction where you're trying to move forward with liquid turning into a gas for water. All right? So let's do this. Let's take a look at some values. Now let me erase this for now. Okay, let me put in some values. So let's do blue for delta H, red for delta S. So for delta H, liquid water, remember it was 285.8. Okay. Gaseous water is negative 241.8. Remember they're in kilojoules per mole, okay? For delta S, liquid water is 69.96 and gaseous water is 188.7. All right. Okay. So, hey, let's find T. So T is equal to delta H over delta S. So let's find delta H. Delta H, okay, by looking at everything else, is really just 1 mole times 241.8. As you can see, I'm not even writing units anymore because I'm so confident. Minus 1 times negative 285.8. Okay, this is very simple. I'm able to do subtraction in my head. So that's 44 kilojoules. I'm going to put in the units right now. Delta S, okay, is 1 times 188.7 minus 1 times 69.96. Okay, and that would be 108.7. But this is joules, so always remember that. That's in joules. Joules per Kelvin. All right. Now that makes perfect sense here. No, hold on. Let me just change this before I forget to change it. Okay, that when you divide these two numbers, you're going to end up with temperature. Okay, because kilojoules and kilojoules would have crossed out. The denominator of a divisor is a numerator. So, hey, let's plug this in. So you have 44 kilojoules divided by 0.1187 kilojoules per Kelvin. The answer should be in Kelvin. Okay, and my calculator says 370 Kelvin. Now don't leave it at Kelvin. Okay, nobody understands Kelvin other than Kelvin and you and I and our chemistry class. So you want to make sure that your temperature is changed back to degrees Celsius, and all you have to do is subtract that by 273. Okay, and your answer is, hey, 97 degrees Celsius. That's very close to 100, like what we would have predicted. So that's how you find boiling point of water. Okay. Anyhow, I'm gonna leave you guys with this question. Okay. Same idea. Calculate the condensation of hydrogen peroxide. Condensation means you're going from gas back to liquid. Okay, let me give you some values here. Same idea, blue for delta H, red for delta S. So H2O2 at liquid state or gas state is negative 136.3. $187.8, and for delta S you're looking at 109. Oh, yeah, I almost made a mistake here. Okay, I'm trying my best not to make any mistake looking at this book. Okay, and liquid H2O2 is 109.6 joules per mole Kelvin. There you go. Okay, so I want you to find out what the condensation point is, okay, for this reaction, meaning that what is the temperature where gaseous hydrogen peroxide will condensate back to a liquid hydrogen peroxide. Let me just give you the answer like last time. That T, this is actually a very bad physics mistake, okay? Never use small t. Always use big T for temperature. Small t stands for time. Okay, this is the answer. Hopefully you guys can come up with that. Anyway, that's it for today. Okay, so this would have been the continuation of topic 5. Really, it's just looking at how to find out if something is spontaneous or not, and to find out, temperature value for certain reaction. Okay, sort of change of state reaction usually, and that's it. So tomorrow we're gonna look at something else. Okay, something that I believe is also very important, called solubility constant. We're going to see if something is soluble or not. And you may be thinking, oh, I know how to do that. Solubility table, dude. Well, not always. I can tell you right now, sodium chloride. You look up sodium chloride in the solubility table, you're going to see, yeah, it's soluble. It's going to dissolve in water. But is there a point where it won't? You can do this experiment right now in your kitchen. Put some salt in water. Keep doing it. Keep doing it. You'll notice that there will be a point where, hey, how come my water is not dissolving any more salt? That is what we want to know. Okay, so tomorrow we'll look at this thing called KSB. All right, have a good day, guys.